McMurtrie from the Swiss National Supercomputing Center, or Centro Svizzero di Calcolo Scientifico, who will just give us a site update. So please welcome.
Thank you, Hussein.
Thank you.
Welcome. Hello, everyone. So yeah, as Hussein said, I'm here to give you the site update. I've recycled some slides from last year and just put some updates on there. Literally, it's a site update. Unlike some of the other sites here that haven't presented for a while, you had the misfortune to have me also last year. So just a quick recap in case some of you are newcomers and don't know what CSCS is. I'll just quickly run through this slide. So there's a picture of our office building and our data center from a drone, I think, from Michele's handiwork there. So we were established in 1991 as a unit of ETH Zurich. So the update here is that last year I said we had roughly 90 people. Now we're over 100. Thomas Scholtes, our director, seems to be very good at getting funding and is enabling us to really grow. I heard our HR manager talking about 110 people or so. Compared to some sites, though, we're still quite small, right? But when I started at CSCS, I think there were maybe 35 people. Hussein is one of the people in the room. Hussein and Vincenzo have been at CSCS for quite some number of years. And see, in your time, I think, guys, CSCS has grown a lot. We have this division also in Zurich. So we have quite a presence now in Zurich with this Scientific Software and Libraries group run by Joost van der Wanderley. He's got roughly 30 people now working there. So we develop and operate the key supercomputing capabilities required to solve important problems for science and or society. This is our hedgehog statement, as Thomas likes to put it. We lead the HPCN strategy that was passed by the Swiss Parliament in 2009. We've run this user laboratory for supercomputing since 2011. So it's programmatic research, as Sadaf said this morning, based on scientific excellence. There's no money changing hands here. If you're an academic and you get a grant to run on our system, away you go. Of course, we monitor your scientific output, and we like to see our high impact publications and so forth, which ETH has many of, so that's good. We have roughly 1,000 users, roughly 200 projects. So I never update these numbers. Maria Grazia is the expert of these numbers. In the past, for one of our projects, we won a Swiss ICT Innovation Award. Just a quick overview of our infrastructure. So our current power and cooling is 12 megawatts. We can upgrade to 25, so we're a moderately sized data center. We're not at the scale of the hyperscale data centers that Sadaf was telling you about this morning, but nonetheless, we're a reasonably sized data center. We're 2,000 square meter machine room. We have this secondary distribution deck here with all of our electrical and cooling distributions, secondary distributions there, and the main deck in the basement. For those of you that don't know, we get our free cooling from the lake, from these submerged intakes. They're at minus 40 meters below the lake, just out from Pakociani, which is just out there. And the water is pumped roughly 3 kilometers or so up to us. So for some of you, I think that's you already know that. I put that there for the sake of completeness. I stole this slide from my head of compute services, Nick Cardo. He put together this very nice slide with this animation. You see the structure there of CSCS. I'm in charge of this HPC operations section. I have 3 groups here. What I'm going to talk to you today is about our medium-term and short-term developments and how we've progressed since I last spoke to you in relation to infrastructure services. Of course, this is only a small part of what we do at CSCS. The main part of CSCS is still driven by our user lab and those 1,000 or so users, and Maria Grazia runs most of that out of her section. We have our CTO here, Sadaf, and she has a group that we call the Office of the CTO. And you can see also this scientific software and libraries of Jos up in Zurich. And then we have our business services that Ladina runs, and Michaeli's in charge of the staff unit. All, very important units that go into making CSCS what it is and how we can keep our daily operations running, but also do these more forward-looking activities. So I've circled this infrastructure and development services group, which is run by one of my guys, Lucas. Most of what I talk to you today about comes from that group, or that group is in some way tied to the developments. Just also a recap about our Daint system. So it's this heterogeneous XC40, XC50 environment. So it's a hybrid XC50, in fact. It's been operational since April 2013. We've done several upgrades and extensions of the machine. I've highlighted here the number of hybrid nodes now has increased since last time. Those of you that have a good enough memory will know that that number now has grown by 384 nodes. I think the total system memory, this number may not be correct now because of these additional nodes, but nonetheless, so the system now has peak performance on the hybrid partition of roughly 27 petaflops, and we measured it at 21 petaflops, and it's still one of the greenest petascale supercomputers on the Green 500 list. These additions to the system came in October of last year, so we added 2 hybrid cabinets to the system as part of the HPP's Interactive Computing E-Infrastructure, the so-called IC project, where we were able, with our other colleagues throughout Europe at 4 other sites, to get a non-trivial amount of funding from the European Commission. And that money, most of it, we put almost immediately into these 2 new hybrid cabinets. And this means that we can now support on Daint, HPP and Prace workloads, which I'll explain a little bit more to you about in subsequent slides. So this diagram here is the same as last time. I just changed the date here, and I've also added this Phoenix logo. So this IC project is the first instantiation of the infrastructure that is being provided by this Phoenix research infrastructure, which is basically an MOU for 5 sites to work together on a federated HPC and compute and data infrastructure in Europe. And I've added the HPP here as now another one of the customers here of the many that we support. Colleagues from PSI, from the University of Zurich. Of course, there's our main activities relating to the user lab. Sadaf has already spent some time this morning talking to you about some of the innovations around enabling workflows for chip on the Daint system. So it's a consolidated HPC environment for various user communities is how we see the Daint system. In relation to the data center ecosystem, this little cartoon is really supposed to show the environment. Of course, it doesn't look like this in reality, but we have the HPC system here, our consolidated Daint system. We have some dedicated customer systems and platforms. There's a system that we house for the Blue Brain project. They manage it themselves. There's the Meteo Swiss system that we host, so we manage it for them. And the system runs their operational workloads, as you heard from Sadaf and also DK this morning. The chip cluster, as you heard from Sadaf, is basically going to go away, at least the compute part of it. There's still some parts of it that we need to keep around, but in terms of the compute, all of that's been migrated to Daint. Of course, we have our site-wide parallel file systems and tape library and TSM as archive. Our data center network, and then in the middle we have our cloud infrastructure. And I want to talk a little bit more about that. I have a few more details compared to last year about those systems, so that's why I highlight those in green here. In relation to the HPC-Cloud Convergence discussion that we've been having today, that these systems are kind of important. So, infrastructure as a service, it really relates to those systems. So, this is our so-called Pollux OpenStack environment. It's we run Red Hat OpenStack there. You can see a schematic here of OpenStack. I'm sure that most of you in the room know this much better than I do. I view this system as a vanilla OpenStack environment with some site-specific optimizations, so connection to our GPFS, so the Swift object storage comes from Swift on GPFS. The network configuration is more security focused because the customers are root on their VMs. And this system hosts hundreds of VMs for domain-specific platforms, domain-specific portals for various services. We have another system which is Fullen, and that's a completely virtualized HPC environment. We spent quite a bit of time working with the Octo colleagues to somehow optimize this system for HPC workloads. The idea is that this environment is one that is more closely managed by us. It's based on Bright Computing's OpenStack. And we spent quite a bit of time getting this system, as I say, to be optimized for HPC, removing some of the various layers in OpenStack to get the performance of the virtualized environment to within about, well, 10% was the goal, 10% of bare metal. I think in most cases we did much better than that. More importantly, we can slice and dice this system how we like. So underneath Fullen is the actual infrastructure. It's a system we call Meetin. I'm sure you guys know this much better than I do, but the whole idea with OpenStack is that you can change how the system, the virtualized environment is configured. You can add more virtualized environments, you can grow and you can shrink them. So this system is actually helping us to navigate this path of software-defined infrastructure. And some of that more forward-looking stuff Sadaf was telling us about this morning. So in terms of our timelines with OpenStack, Marco, who's sitting here in the back, he put together this slide when we had an exchange with our colleagues at CEA in Paris just recently. I quite like this slide because it shows that really we started with OpenStack at CSCS back in 2016. We did some feasibility evaluation. We set up this Tambo proof of concept deployment. We interacted with a Red Hat consultant who came in from Milan. By May of 2017, we had this production deployment ready. TDS was set up. After that, the goal was to get the production system set up as quickly as we could. So that's why this is kind of a little bit reverse. You would think you'd set the TDS environment up first and then do the production, but we really focused on the production environment. And then we started really to host services for the Human Brain Project there, which really desperately needed them. In 2018, we started on this OpenStack for HPC. So performance optimized environment, the so-called Meetin system. And that was a pretty successful project. By December of 2018, we were starting to, well, we'd been working already for months to work out how to upgrade the Pollux environment in situ. Red Hat recommended that we buy new hardware, install the new environment there, and then migrate everyone, and we really didn't want to do that. So Marco and the guys spent months preparing Pollux for an upgrade, And then in January of this year, that upgrade was completed, and now we can stay on this SP13 version now until that system reaches end of life. So, support for Docker containers in the theme of HPC-Cloud Convergence. Now, I spoke about this last time. There are some updates, though. So, currently in production on Daint, we have Shifter, actually our flavor of Shifter, which we've called Shifter NG for next generation. And this is in production doing thousands of container launches a day. I've got some plots and subsequent slides to show you that. And so this has been working pretty well, I would say. We learned a lot about how not to do, well, things that you should and shouldn't do for software productization, to make sure that all interested all stakeholders in the software environment are aware and on board with the changes and the deployment of that software. So you all understand the reasons for this fascination with Docker containers. So the idea is that it's convenient for the user. You can build and test your containers on your laptop, and then you can run them securely with high performance using Shifter on our hybrid system. With native GPU and MPI performance. These are the goals, these are what the guys have achieved. In some cases, you get even improved parallel file system performance for some applications like Spark, because the workload, it looks like one big file to the file system as opposed to thousands of little ones, is what the guys tell me. And as Sadaf told us this morning, we have many different use cases. There's this LHC on Cray, and I just reference you to her much more comprehensive slides from this morning about that. We've got the HBP workflows. We have some data analytics frameworks, and as I said before, we have these, a few thousand container launches a day, which I can show you on this next slide. So I don't expect you to drill into the details here, but I asked Nick some months ago to tell me how much Shifter is being used on Daint. So he chose the period from April through to September of last year, so a 6-month period or thereabouts, and just did counts of the number of container launches. And so, not such a trivial amount on this day here. We have, more than 9,000 container launches. This is just for the chip community. And at the moment, they still are the biggest users of Shifter. By contrast, CMS, which is one of the experiments that Sadaf told you about from LHC, they use Singularity. We also support Singularity on the system, and we're also getting similar numbers of container launches for Singularity on the machine for the same period. But now it's time to change up. So at CSCS, we're now looking to next generation support for Docker on our system. So what we're focusing now on is what we like to call community fostering. So we want adoption of standards, so this Open Containers Initiative, so-called OCI compliance. We want to leverage existing tools available in existing ecosystems, so this means authoring tools, associated documentation, public repositories, all of those good things. We need, and we want vendor support. We want, the support from NVIDIA for their GPU software environment. We don't want to be having to do that ourselves. We need Cray's MPI software environment. We need DK's RDMA, GPU Direct, to get the high performance out of our hybrid system. We also need improved image management. We learned a lot of lessons with how Shifter does the image management, and one of the big efforts that Lucas's team put in was actually to rewrite the image gateway for Shifter. That's what's used in Shifter NG. We're targeting petascale performance for containerized applications. We've been doing a lot of scale-out runs actually just recently on the system, and there's an upcoming paper that you can expect for that, so watch this space. I can report that we're making some quite nice progress in that direction. And so we target a production deployment of a thing that we're calling SARIS. SARIS is a large crane. So we wanted to use crane as the name for this thing. Cranes are used on the wharf to lift containers, but someone had already had that great idea years ahead of us, so we chose SARIS as the name instead, and we're targeting summer of this year for this to be in production on the system. And so if you want to know much more of the details, please go to Kian's presentation on Wednesday. SARIS, an OCI-compliant container runtime for HPC. It's at 1:30 in Sale B1. And he will really drill into the details there. I think he has comparisons with other runtime environments. You'll get the full 9 yards from him there. This was really just a little teaser from my side. So, another piece in the puzzle of this HPC cloud convergence is exposing legacy HPC infrastructure to cloud-based environments. We're also making some developments in that direction, so I'll just quickly explain some of those. So, connecting HPC and cloud environments, there's obvious limitations with the legacy HPC software environments, which mean they're not really compatible with cloud environments. I think we all know that. There's a lack of standardized RESTful APIs. There's a lack of support for fine-grained role-based access control mechanisms. This implies fine-grained authorization. HPC traditionally uses access control lists and POSIX permissions. Those don't really cut the mustard in the cloud world, and we need a solution for that. There are also interactivity limitations. So HPC's traditional workflows are based around what Lucas and I discussed earlier in the day, more serial processing. So users interact with the machine and they use SSH, they submit batch jobs, but really you need a human in the loop here. Someone's at a keyboard, submitting jobs, waiting for output. It's more serial in fashion. Also, we have at our centres a number of legacy user tools that are really written for interaction in the shell. How does a domain-specific portal get access to those tools with fine-grained access control so that they are only allowed to see the things that they're authorised to see? And also another aspect of human-in-the-loop type thing is the moving of data between HPC file systems is often some user-driven activity. Someone runs an HPC simulation, it produces output on the scratch file system, and then they have to copy it to another file system to process it. We have a data mover cluster for that, but it involves scheduling chain jobs. So the job on the HPC system runs, once it's finished running, then the other thing starts, but someone has to write those batch scripts, and they're user-specific. So how do we address these problems? Of course, we're not the only centre facing these challenges. There's several people in the room from centres that are also trying to face this challenge, and in some cases probably even far more advanced than we are. We've looked at the current solutions and we don't think that they really fit our requirements. And so in late 2017, like around Christmas time, really more like January 2018, we took the decision to develop our own middleware for the purpose of connecting HPC and cloud environments. And so I'll explain to you a little bit more about that. That's my last slide. How am I going for time? I guess I'm way ahead of time, or? I think you are. Okay, well that's good. So as Siddharth explained this morning, we have a number of existing workflows that need things like access to HPC file systems from cloud-based platforms, access to HPC compute resources in an interactive manner, support for role-based access control mechanisms with authorization when accessing your HPC resources, be they compute, file systems, tools, whatever. They need access to these user space legacy tools in the shell. And so our in-house developed middleware will enable these types of workflows. So things like Jupyter Hub style workflows as an example of interactive HPC, system-to-system interfaces. So this enables the building of additional services on top of HPC infrastructure. So one system is doing work on behalf of a user in an authorized, completely authorized and secure fashion with another system so that things are automatically ready for users when they open their portals. And this takes us a step closer. It's not all the way there yet. We've still got a lot of things to learn. But it means that we're using HPC infrastructure to deploy non-traditional HPC workloads. Deep learning is just one example of that. So you can expect an announcement about that very soon. Some of you will be going to CUG. You can expect some papers at CUG about this. For those of you that aren't, you'll hear about it outside of CUG, but the CUG community will be the first to hear about this. The development is quite a long way along. The software work is largely done. We're spending a lot of time on the authorization layer. That's really challenging us at the center. It's really forcing us to have to examine our AAI. But I feel that we're making progress there. So that was all I wanted to talk to you about today. That's the end of my presentation. Thank you. Okay, thank you. Oh, sorry.
I have just one curiosity, not a real, let's see, important question. Which was the code to move from shifter to shifter? So what he needed that was not given by.
So Lucas knows much better than I do, and I'll look at him while I run off the list. But it was things like support for GPUs, support for MPI. The image gateway wasn't really up to scratch and had to be really completely rewritten. Those types of things. There's probably others, Lucas. No, he's given me the thumbs up, so maybe I got that maybe 80% right. And yeah, so we worked with NERSC on this. You know, they're fully aware of the work that we've done. Maybe they don't see eye to eye with us about some ways we proposed to do things, and some ways we basically, let's say, bloody-mindedly just went ahead and did it. But yeah, that's kind of the history. Okay. Anyone else? Good, okay. Thank you.